Uniswap V3 does not store the price. It stores the square root of the price as a fixed point number in a uint1. Unchecked isn't an optimization here, it's a correctness requirement. That's a rule you'll apply against 3 tiny functions, and every mint, every burn, every swap you write for the rest of this module runs straight through them. Okay, open the Uniswap V3 pool contract, look for the variable that holds the price, and you won't find it. Uniswap V3 does not store the price. It stores the square root of the price as a fixed point number in a uint160. And that sounds like the kind of thing an engineer does to be clever. It isn't. It's the single decision that makes the entire swap loop cheap enough to exist. So this is section 2 of Building Uniswap V3 on the Zealynx Academy, and it's the first one where you actually write code. Before you can build a pool, you need V3's coordinate system, how price is stored, how price space is indexed, and the guardrails that keep both inside safe bounds. Let's start with that square root. Last episode we had a relationship for a swap. With liquidity L, if you add some amount of token 1, the price moves so that the change in the square root of P equals that amount divided by L. Read that again, because it's the whole point. The change in the square root of the price is linear, not the price, the square root. So if the pool stores the square root of the price, every step of a swap is 1 multiply and 1 divide. That's it. If it stored the price directly, the contract would have to compute a square root on every single swap on chain, and square roots are iterative and expensive. So V3 pays the square root cost exactly once, off chain, when a human picks a price. The chain only ever sees the result, right? That's the trade. Now why 96 fractional bits? Q64.96 means 64 integer bits and 96 fractional bits. Add those and you get 160, which is exactly the uint160 it's packed into. V3 supports prices from 2 to the minus 128 up to 2 to the 128. Take square roots of both ends and that range becomes 2 to the minus 64 up to 2 to the 64. So the integer part needs exactly 64 bits. No ways, no shortage. And the fractional part, 96 bits, leaves you 32 bits of precision, even at the very bottom of that range. The type isn't an accident. It's the largest square root price that still keeps the intermediate math inside a uint256. Let's make it concrete. Say the price is 2. The square root of 2 is about 1.414. Multiply that by 2 to the 96th and you get roughly 1.12 times 10 to the 29th. That enormous number is what the pool actually stores. And to get the price back out, you divide by 2 to the 96th and square it. You'll do that squaring constantly when you reason about V3, so get comfortable with it now, okay? So that's how price is stored. Now, how is price space indexed? Concentrated liquidity needs boundaries you can name, so V3 indexes price logarithmically. Tick I means a price of 1.0001 raised to the I. Every tick is 1 basis point away from its neighbor, 1/100th of 1%. And because the spacing is logarithmic, a tick is the same relative step, whether the price is 10,000 or 10,000, which is exactly what you want for financial ranges. Tick 0 is a price of 1. Tick 6931 is a price of about 2. Tick minus 6932 is about a half, and that supported price range translates into a hard limit. Minimum tick is minus 8.87272. Maximum tick is the same number, positive. The library that converts between ticks and square root prices is called TickMath, and it's handed to you. 20 hard-coded magic constants. You use it, you do not retype it. But read it once, top to bottom, and notice its revert codes. A capital T for a tick out of bounds. A capital R for a ratio out of bounds. V3 uses these tiny strings everywhere because back in 2021, reverse string bytes cost real deployment gas. Every V3 fork you will ever audit inherited them. Now not every tick is usable. Each feed tier imposes a tick spacing. In a 0.3% pool, spacing is 60, so positions may only use ticks divisible by 60. Why? Because every initialized tick a swap crosses is an extra storage right. Coarser spacing means fewer ticks. that can be initialized, which caps how expensive the swap loop can get. But spacing does one more thing, and this one is a safety property. The pool tracks total in-range liquidity as a uint128. If every usable tick were allowed to hold the maximum, the sum could overflow. So the pool computes a cap once in its constructor. Round the minimum and maximum ticks inward to usable ones, count how many there are, and divide the uint128 range by that count. For spacing 60, that's 29,575 usable ticks and a cap of about 1.15 times 10 to the 34th per tick. Enormous. The cap is in there to constrain liquidity providers. It's there, so overflow is impossible by construction, instead of being checked in the hot path. That's a pattern worth stealing, by the way. The best invariant is the one that can't be violated, not the one you test for. If you're finding this useful, this is exactly what we do inside Zealynx Insiders. Live build sessions every week, where we work through protocols like this one together, and office hours where you bring your own code. Links below. Right. Now the piece you're going to write. Liquidity is stored unsigned as a uint128, but changes to it are signed. A mint adds, a burn subtracts. So you need a function that applies a signed delta to unsigned state and reverts if it would wrap. Here's how V3 does it. If the delta is negative, subtract it and require the result is strictly less than what you started with. If it isn't, the subtraction wrapped around. So revert with ls, liquidity sub, and symmetrically for addition with LA. Now look at that carefully, because there's a trap. In Solidity 0.8, that subtraction would revert on its own, with a bare panic, before your require ever runs, which changes the behavior. Callers expecting less get a panic instead. Tests break. Integrators break. So you wrap the body in an unchecked block, and you let V3's original comparison do the checking. Unchecked isn't an optimization here, it's a correctness requirement. That's a rule you'll apply again and again in this module, so mark it. And the last one is the smallest. Every position's range passes through three requires: lower tick below, upper tick, or TLU. Lower tick at least the minimum TLM. Upper tick at most the maximum TUM. That function is the only gate between user-supplied ticks and the math libraries. Remove any one of those three lines and you can mint a position whose amounts are undefined. So let's write them. Three tiny functions, and every mint, every burn, every swap you write for the rest of this module runs straight through them. Unchecked block first, then the negative branch, subtract and require it got smaller, ls. Then the positive branch, add and require it didn't get smaller, LA. Now the cap, round both bounds inward, count the usable ticks inclusively, and divide the uint128 max by that count. And the three requires, verbatim codes, keep them exact, and run it 9 out of 9. That's the coordinate system done and 10 links on the board. So, you now have the two things every remaining section leans on. Price as a square root in Q64.96 and price space as ticks 1 basis point apart with the guardrails you just wrote. Next episode is SqrtPriceMath, where those square root prices stop being storage and start doing work. Given a price range and an amount, how much of each token does a position actually need? That's where the rounding starts to matter, and where getting it backwards hands money to the wrong side. See you there.